Hello students, in the last lecture we have studied about the wave propagation in a free space. So now we will see about the Poynting theorem and wave power. Actually, by means of electromagnetic waves, what is done is energy can be transported from transmitter to receiver. The energy is what we can do is we can store in electric field, also we can store in a magnetic field. Is transmitted at a certain rate of energy flow from which can be calculated with the help of Poynting theorem. So as we know, E and H are the basic fields. E is electric field expressed in volt per meter, while H is the magnetic field expressed in the ampere per meter. So if we take the product of the two fields dimensionally, we get volt ampere per meter square or watt per meter square. So this product of E and H gives a new quantity which is expressed as watt per unit area. Thus this quantity is called as power density. So actually we want a power density. So here, you can take either the both E and H vectors as a dot product, or you can take a cross product. If you take a dot product, you will get a scalar quantity, but a power flows in a certain direction, so therefore it is a vector quantity. So therefore, in order to find a power flow associated with electromagnetic wave as it is given in the slides, I am going through that. Now it is necessary to develop a power theorem for electromagnetic field known as a Poynting theorem. So it was originally postulated in 1884 by an English physicist John H. Poynting. So the development begins with one of the Maxwell curl equations in which we assume the medium may be conductive. So before going to that, I want to tell you a Poynting vector is also can be expressed. That is nothing but vector P is equal to E vector E cross vector H. That is nothing but a Poynting vector. He stated that cross product of E and H has nothing but a Poynting vector. So now let us go through this theorem. Now development begins with one of the Maxwell curl equation in which we assume that medium may be conductive. Therefore del cross H is equal to J plus dou D by dou T, equation number 63. Now next we take the scalar product of both sides of the above equation with E. So E dot del cross H, that is equal to E dot J plus E dot dou D by dou T. Now what we do next is we then introduce the following vector identity, which may be proved by expression in rectangular coordinates. That is del dot E cross H is nothing but minus del dot E dot del cross H plus H dot del cross E. This is equation number 65. Next, using the equation 65, the left side of 64 is nothing but H dot del cross E minus del dot E cross H is equal to J dot E plus E dot dou D by dou T. So you can use the equation 65 in the left side of 64 results in equation 66, where the curl of the electric field is given by the other Maxwell curl equation. This del cross E is equal to dou B by dou T. So here minus H dot dou B by dou T is minus del dot E cross H is equal to J dot E plus E dot dou D by dou T. Or minus del dot E cross H is equal to J dot E plus epsilon E dot dou E by dou T plus mu H dot dou H by dou T. So this is equation number 67. Now the two time derivatives in 67 can be rearranged as follows. So epsilon E dot dou E by dou T is nothing but dou by dou T into bracket half of D dot E, and mu H dot dou H by dou T is equal to dou by dou T into bracket half of B dot H. So this is equation number 68b. Now equation 67 becomes minus del dot E cross H is equal to J dot E plus dou by dou T half of D dot E bracket complete plus dou by dou T into bracket half of B dot H. This equation becomes equation number 69. So next, finally we integrate equation 69 throughout the volume, that is minus integration over volume del dot E cross H dV is equal to integration over volume J dot E dV plus integration over volume dou by dou T half of D dot E bracket complete dV plus integration over volume dou by dou T into bracket half of B dot H dV. So therefore this equation we get the divergence theorem is then applied to the left handed side, thus the converting the volume integral there into an integral over the surface that encloses the volume. On the right hand side, the operations of spatial integration and time differential integrations can be interchanged. So thus the final result is integration over a closed surface area E cross H dot ds is equal to integration over volume J dot E dV plus d by dt integration over volume half of d dot E dV plus d by dt integration over volume half of B dot H dV. So this is the final result of what equation, and this is the equation number 70. So whatever you are seeing in this equation 70, it is known as a Poynting theorem. So whatever you are seeing in the equation on the 70, it is nothing but considered as a Poynting theorem, right? The sum of the expression on the right must therefore be the total power flowing into this volume, and so the total power flowing out of the volume is integration over area E cross H dot ds. That is equation number 71. The total power flowing out of the volume is this one, and total power flowing into this volume is which is given in the right of that equation number 70. Now where the integral is over the closed surface surrounding the volume, the cross product of E and H is known as Poynting vector, that is S, or we can call it as P. So therefore S is equal to E cross H watt per meter square. So this is a Poynting vector. Hence what we have done is we have proved this Poynting theorem, and that is what which gives us the equation number 70 as a final result over the all the results by considering the Maxwell equations, one in the form of one you can see in the form of Maxwell curl in the electric field, and one more it is in the form of Maxwell curl in the form of magnetic field. So hence we have proved the Poynting theorem, where Poynting theorem can be used for the calculating the powers in the electric field as well as magnetic field. Thank you.